Hi there. So today, in today's lecture, I would like to talk to you about RL circuits, and that's a circuit, of course, with a resistor, an inductor, and also switches and batteries, and the equations that govern their use. So first, the basics. In previous lectures, we've been talking about inductance. Specifically, the last two lectures, we talked about mutual inductance and self-inductance. And so now, when I refer to the term inductor, what I mean is an object that has a large self-inductance. In fact, it has such a large self-inductance that the inductance for the inductor dominates over any other kind of inductance that might be present in the circuit. Okay? This is important to remember, though, that even without an inductor coil, a circuit is going to have some self-inductance. It just might be negligible without that large self-inductance that comes from the inductor. Now, the symbol that we'll use in circuits for an inductor is a curly line, as is shown here. So it might look to you like a little tiny solenoid, for example. And some commercially available inductors are solenoids, and some are, of course, toroids. Now, in previous lectures, we introduced the equation for the back EMF that results from the self-inductance of an inductor. So here, let's remind ourselves of that equation. The back EMF is equal to minus L di dt. So here, L is the self-inductance of the inductor, which is resulting from geometrical considerations primarily, and physical properties of the inductor, such as the number of turns. And di dt would be the change in time of the current. Now remember, the inductor in a circuit opposes changes in that circuit. The inductor attempts to keep the current the same way it was before the change occurred. And this resistance to change can cause the circuit to be less quick to respond when changes occur. So here's a little schematic of an RL circuit. You can see here that you have a battery with some EMF. You have some switches. Here you have S1 and S2. You have a resistor and you have an inductor. So this is a pretty straightforward, simple circuit. And we're going to derive the equations for inductors and circuits based on this simple one, and then we'll talk about other things like how to add more inductors into circuits and so on and so forth. Okay, so here we go. Let's assume that switch S2 is connected here at A, and B isn't connected. So that would make this branch right here not important for now, and the current would flow clockwise around the circuit once switch S1 is closed and would not go through that middle path. Okay, so now let's say that we, at time t is equal to 0, close that switch. And of course, you start to get current flowing clockwise around the circuit. But what happens is, when that switch is closed, of course that causes a quick, abrupt change in current, which the inductor will want to oppose. So let's find the equation for what the current is like with respect to time for this circuit. So in order to do that, I'm going to apply Kirchhoff's loop rule. So here we would have the EMF of the battery would be the positive EMF, and then the voltage would drop across the resistor. So that gives you a minus IR term. And then the inductor would generate a back EMF. And so if you applied your total loop rule here, you would have EMF of the battery minus IR minus L di dt, and then that would equal to 0. So from your textbook, Purcell and Morin's textbook for electricity and magnetism, in Chapter 7, Problem 14, they ask us to solve that differential equation and find the current with respect to time, or actually prove that the current with respect to time is what they say it is in the textbook. So let's go. Okay, so here we have, rearranging the equation from the loop rule for the previous page, EMF minus IR is equal to L di dt. Now, this is a simple first-order differential equation here. So what we're going to do is we're going to group terms so that all the terms that have the current are on one side of the equation, and stuff that doesn't have current is going to be on the other side. So to do that, I'm going to multiply this equation through by dt, and then I have EMF minus IR times dt is equal to L di. Now, EMF minus IR, that contains the current, so I'm going to divide that out from both sides. And then I end up with dt is equal to L di over EMF minus IR. Now I have it grouped correctly, so I can integrate both sides of that equation. When I do that, I'm going to solve for the current I at some time t. Now remember, the current starts at 0 and increases to whatever the value is at time t. And then my time is going to start, of course, at 0 when I close the switch. That's when I define t is equal to 0. And then I just want to know what the current is at some later generic time t, so I'm going to integrate my dt from 0 to t. Therefore, the limits of the integration on the right-hand side have to be the current starting at 0 and going to whatever it is at some later time, which would be I. So now I have the integral from 0 to t of dt, and that's equal to the integral from 0 to I of L di over the EMF minus IR. You can do a pretty simple substitution to solve this integral, okay? So I used y is equal to EMF minus IR, and then that would make dy minus R di. So then plugging in, using that substitution, I end up with minus L over R, integral of dy over y, and of course the integral of 1 over a thing is the natural log of that thing. So here I have minus L over R natural log of y. Now, I never, when I do this, maybe it's a little lazy, but I go ahead and then do my substitution, and then I put back in what my substitution was, and then I plug my limits in. I could change the limits of integration, of course, and that would probably be what your calculus teacher would be. But laziness wins the day here. So now I'm going to say, okay, integrating dt from 0 to t, I get t, and now plugging back in for what y was, minus L over R times the natural log of EMF minus IR, and now I can use my original limits of integration, which was 0 to I. Okay, so remember that this would give us the natural log of EMF minus IR minus the natural log of the EMF, if you take I is equal to 0 when I evaluate my limits. But when you subtract natural logs, you can take the ratio of the arguments. So, rearranging here and multiplying both sides by negative R over L, I end up with negative RT over L is equal to the natural log of EMF minus IR over the EMF. Okay? Now remember, this is the battery's EMF. All right, to get rid of that natural log, I raise both sides to e, and I have e to the minus RT over L is equal to the EMF minus IR over the EMF. Rearranging that equation, I end up with EMF minus EMF times e to the negative RT over L is equal to IR. And then solving for I, which is divide out by R on both sides, I end up with the equation for I of t is equal to EMF over R times 1 minus e to the negative RT over L. Okay, so I think I broke the steps of the algebra there into little bite-sized chunks. But if you need to pause the video at any time to see that you can follow that math, make sure that you do that, okay? In the meantime, we've done what Purcell and Warren asked us to do, which is derive that equation with respect to time for the current. Okay, so we can also think of the coefficients in the multiplying time in our exponent as the time constant, okay? So then we would call our time constant, which is generally abbreviated with the tau, as L over R. Now physically, this time constant would be the time required for the current to reach 63.2% of its maximum value. So what I mean by that is, if you look at the plot of the current versus time, the max current would of course just be like the inductor wasn't there. So that would be the EMF of the battery divided by the resistance. And you can see that the current, which is indicated here in the orange curve, is going to increase towards that limit, okay? And it's going to increase in an exponential way. So here the time constant is marked, and you can see that 63.2% of the max is where tau is marked here, okay? So eventually, it'll reach that limit. It does increase very rapidly depending upon your time constant approach that equilibrium value. Now, if you didn't have an inductor, then what would happen is that your exponential term would go to 0 and your current would instantaneously reach its max value as expected. It's important to understand, though, that since every circuit does have some self-inductance, even if there's no inductor in there, this never happens, okay? Even if the time constant is very short, there will be that exponential increase towards the theoretical value, EMF over R. Now, if you were to plot the time rate of change of the current, you would see an exponential decrease. In other words, the di dt would be very large at first, but then it would exponentially decay towards 0. And then that would be given as di dt is equal to EMF over the self-inductance L times e to the minus t over tau, where tau is your time constant. Okay, now let's talk about what happens if you had that switch S1 closed for a long time and you had the switch S2 in position A for a long time, all right? So at that point, and we'll talk more about this expression later, you've stored a lot of energy in your inductor, okay, in the form of the magnetic field present in the inductor. But then you go ahead and move the switch S2 to position B. And this kind of dodges the battery here, and now you're going to have a current flowing through the right-hand side of this circuit with no battery. And then it'll do that until all the energy that's stored up in that inductor is dissipated in the resistor. Yet again, we'll talk about the equations for the energy stored in the inductor in a later lecture, but for now, please understand that that is where the energy that's powering this circuit is coming from, the energy stored in the inductor. In this case, if we had the Kirchhoff's loop rule equation, we wouldn't have the battery in there. And we would end up with minus IR times minus L di dt is equal to 0. So what we're going to do is yet again derive an equation for the current with respect to time for this. So moving forward here with that, I can rearrange this equation. L di dt is equal to minus IR. And then put everything with I in it on one side and everything without it on the other. I've got di over I is equal to minus dt r over L. Now I would integrate both sides of this equation. And remember that in this case, the current in the circuit starts off at some value, and then it would have to decay to 0. So the limits of integration on the left-hand side for the current would be I naught, where I naught is whatever your initial current is. And then we want to find out what the current is at some later time t, and I'll just call that I. So I'm integrating from I naught to I of di over I, and that gives me the natural log, right? And evaluating my limits, it would give me the natural log of I over I naught. Now that has to equal to my right-hand side, which is negative r over L, 0 to t, right? I'm going to assume that I change that switch at time t is equal to 0, for example. And then I want to know what it is at some later time t. So I'm integrating from 0 to t dt. And of course, that just gives me t. So my right-hand side integral would equal to minus RT over L. And then yet again, what I'm going to want to do is raise both sides using the exponential. That would cancel out the natural log on the left-hand side, and I end up with I over I naught is equal to e to the minus RT over L. And then I just multiply through by I naught. So you can see that, as you probably suspected, the current exponentially decays from whatever its initial value was, which I called I naught here, okay? And it'll eventually go to 0. According to the equation, I is equal to I naught e to the minus RT over L. So that's what happens when you have a circuit with a charged up inductor. It's not really charging up. The energy stored in the inductor in the form of the magnetic field, right? And then it decays off to 0. All right, so what do we do if we have multiple inductors in a circuit? So let's derive the equations for how you combine the inductances in series and parallel. So let's do series first. If you have several inductors hooked up in a circuit, like you can see here, where L1, L2, and L3 are hooked end to end, then you can apply Kirchhoff's rules here. Now remember that the voltages, when they're in series for components, they add up, right? And so what you would have there is that the back EMFs would add. They would add together. So your equivalent back EMF, which I've called here EMF EQ for the subscript EQ, is equal to minus L1 di dt minus L2 di dt minus L3 di dt. And that would have to equal whatever the equivalent inductance was, minus LEQ times di dt. It's also important to remember here that because these things are in series, the current through all these inductors would be the same, and I've just called it I. So now what I can do is just take the middle and the right-hand side of that equation there and equate them, and you can see that di dt appears in every term, and so I can cancel it out. And the minus sign appears in every term too, so I can cancel that out as well. And then that leaves me with the equation for what you would do for inductors in a series. The equivalent inductance, which I've called LEQ, is equal to L1 plus L2 plus L3. So when you have inductors in a series, you just add the self-inductance together. Now let's look at parallel, okay? You can see here that I've got 3 inductors in little parallel branches all by themselves, so it's easy to understand what's going on here. As we've discussed before, the voltage across parallel branches has to be the same. And what will happen here is, let's say that you have some current I coming out of point A and then flowing out of point B. Well, the junction rule would apply there. So if you have current I1, I2, and I3 flowing through inductors 1, 2, and 3 respectively, then what you would see is that I would equal to I1 plus I2 plus I3 because of the junction rule. If you take the derivative with respect to time of both sides, that would give you di dt is equal to di1 dt plus di2 dt plus di3 dt. So that's the time derivative of our junction rule. Now the voltage drops here are, of course, as I said, equal because the branches are parallel. So that would mean that whatever inductor I had to plug in there, some equivalent inductance called LEQ, right? The back EMF from that equivalent inductor, which would be dependent upon the current I that flows into the junction, that would be minus LEQ di dt. That has to equal what's happening in each parallel branch because the voltage drops are the same. So I would have minus L1 di1 dt has to equal to minus L2 di2 dt, has to equal to minus L3 di3 dt, has to equal to minus L equivalent di dt. So if I take each branch individually and I solve for di1 dt, for example, then I would have di1 dt equals LEQ over L1 di dt. The minus signs would cancel out. Now I can take that value of di1 dt and plug it back into the time derivative of my junction rule. When I do that, I end up with di dt is equal to LEQ over L1 di dt plus LEQ over it's supposed to be L2 di dt, plus LEQ over L3 di dt. And then what would happen is that each one of those L1, L2s, and L3s, the LEQ would cancel out for each one. The di dt appears in each term, okay? And then I would have 1 over LEQ equals 1 over L1 plus 1 over L2 plus 1 over L3. So each of those parallel branches would be the same. Sorry, this is bothering me so much, I've got to fix it on the fly. Here we have L1, L2, and L3, okay? Now going back to my slideshow, there we have it. Now it looks right, okay? All right, so that'll be on the slides that you see for the class. Sorry about that. All right, so to summarize, let's sum up what we've learned. Now in a later lecture, I'm going to do an example problem for you, but I didn't want this one to drag on too long. Maybe it's too late for that, but I didn't want it to drag on too long, so I decided to put the example in a later lecture. But here we go. What we've learned so far is that the current in LR circuits or RL circuits, whichever you want to put first, it's got an exponential dependence. This is kind of similar to the circuits for capacitors. Of course, the equations aren't exactly the same, and I'm not saying that, but the exponential dependence is similar. Now, if you combine inductors in a circuit, that obeys similar equations to the combination of resistors in a circuit. What I mean by that is, of course, if you have resistors in series, they add, just like inductors in a series, you add the inductance. And if you have resistors in parallel, then what you do is you take the reciprocals, you add them up, and then you take the reciprocal of that. And this is the same for inductors in parallel. Okay? All right, so I hope you understood all that, and I'll see you around.